Okay. So last week we looked at working with distillation columns in Aspen, and we specifically looked at using the DSTWU and then the radfrag blocks. So starting with a shortcut model and then transitioning to a more rigorous model. So today we want to look at reactors, and we can have something a bit similar. We have some models that are more simplified, and we have the ones that are very detailed. You would have to get a lot of kinetic data to feed into the block or into the model for it to run. So we'll start with the simplified ones today, and then probably next week we'll look at the more rigorous ones. But I think after today's discussion, we would have done enough so we can have our first assignment. Okay, so we are looking at reactors in Aspen. When we talk about a reactor, we know that it's an equipment in which reactions are going to occur. So we have some chemical species in there, and then they are going to lose their chemical identity. We would have other things being formed in our system. And we are going to look at the different models that we can use in Aspen to simulate reactions. So if we come to our model palette in Aspen, we would see these blocks or these equipments under the reactors section. So we have R stoic, R yield, R equal, R gibbs, CSTR, plug, and then batch. And they are all used for different things. They all have specific things that they are good for. So when it comes to the details for them, R stoic, we've seen it before. We use that one when we have a stoichiometric reaction. We know the conversion, we know the extent of the reaction. For R yield, if we know the yield that we are expecting for our outlet stream, especially for our outlet stream, we can use R yield. Then we have R equal, which is usually for equilibrium reactions. So we have some equilibrium reaction in our system. We can use that. And then for R Gibbs, we usually use that one to help us determine what possible products we can get that would be very stable. So it works based on the Gibbs free energy minimization principle from thermodynamics. So it considers all the compounds that you have in your specification. Before we start the simulation, it considers them or very specific ones you choose. And then it determines which ones are more likely to be formed, which ones will be the most stable at the conditions that you would give the reactor. Right. Then we have the more rigorous ones, the CSTR, the plug flow reactor, and then the batch reactor. So for those ones, we need a little bit more data to do their specifications. So as I said, we've already seen how to use R stoic before. I think that was in our second discussion or so. So we'll quickly go over that one so that we can spend more time on the others. And as we said, for this one, we need to have our stoichiometric equations, and we need to know maybe the extent of the reaction or the fractional conversion, and then we can pick it up from there. So we'll use an example to really tie everything together. We have sweet natural gas, 90% is methane, 5% is ethane, and then 5% is propane. And we are being told that it is burnt in a combustion chamber of a gas turbine with excess air. And that's 200%. So it's in excess of 200%. Using our stock to simulate the process, if we have the combustion chamber operating adiabatically, then the temperature of the exiting gas, and that's the second case. So we want to do the simulation again when the temperature of the exiting gas cannot exceed 1100 degrees Celsius. So the assumptions we are using are the chamber operates at 20 bar, and then the feed would enter the chamber at 30 degrees Celsius. So these are the things that we are going to consider. Now, if you look at, okay, I think before we do that, let's first try to determine what components you will need. So in Aspen, when you are specifying your components, like we said before, you need your reactants, you need your products, you need any inerts that you may have. So you need to have all these things down. You don't leave any of them out. So you don't just specify the reactants and assume that that is all. Right? You need to specify both reactants and products, and then any non-reacting species that you might have in your system as well. You need to specify all of that under your components. So if we look at this, we have methane, ethane, propane, and we are burning it in excess air. So we know that the products you should be expecting should be carbon dioxide and water because we are burning these gases or these hydrocarbons in excess air. So we're expecting carbon dioxide and then water, right? So if we are to do our specifications, so we can come to Aspen. Oh no, sorry, and use simulation instead. So we can come to Aspen and then we can specify all of them. So methane, propane, and we know that we need carbon dioxide and we need water as well. Okay. Now we are also burning it in air, so we need some oxygen and nitrogen too. So you need to really be very particular about the things that you be specifying. So we need oxygen, we need nitrogen, and then we can take it from here. So we'll now specify the property method. We'll work with Penn Robinson. We'll click on next. This is just some binary data Aspen is putting together. So we just run it. And then we can now come to the simulation interface itself. Now, let's get back to it. You realize that the question has given us an idea of the temperatures, the pressures that we should work with, but we've not been given anything with regards to flow rates. So we need to do a little bit of calculation to get that down. So we can assume a basis, maybe 100 kilomole per hour of natural gas. We can do that. But then if we should do that, how much air are we going to use? Right. So if we want to do the calculation, we first need to get our balanced equations, and then we can now pick out the theoretical amount of air we will need, and then we can find how much it would be if it was supposed to be in excess. So if we should burn all these gases, methane, ethane, and propane, these would be the balanced equations. And we see that for every mole of methane, we need 2 moles of oxygen. For every mole of ethane, we need 3.5 moles of oxygen. For every mole of propane, we need 5 moles of oxygen. So we can use this to determine how much oxygen we'll need theoretically. So if we are using a basis of 100 moles of natural gas, how many moles of methane do we have? We're told that methane is 90% of what we have in there. So that's for methane. So if it's 100 moles, then 100 kilomoles, 90 kilomoles or 90 moles, whichever basis we are using. So here it's in moles. So 90 moles would be for methane. So if 1 is to 2 moles of oxygen, then 90 would be equal to 90 times 2. So that's why we have this here. Sorry, that's why we have this here. Then we do the same thing for ethane. So it's 3.5 times 5 because 1 is to 3.5. So if we have 5 moles of ethane, we'd have to multiply by the 3.5 to get the number of moles of oxygen we need there. Then we do the same thing for propane, right? Is 1 here is to 5. So if we have 5 moles of that, we'd have to multiply by 5 to get that. So we'd have, if we should put everything together, we'll be getting this. I think when I tried it, I had 222.5, but you can confirm. Okay. So now that is what we are going to get if we should have the stoichiometric amounts needed, just the right amount of oxygen needed. But we're told that we need it in excess, and then the excess is supposed to be 200%, right? So if this was giving us 100%, then we'll have to multiply by 2 to get 200%. So the actual amount of oxygen, we multiply that by 2. That's why we are getting this value. But remember, we are not just burning it in pure oxygen, we are burning it with air. So if this is the amount of oxygen we have, then we need to now know the amount of air we need, right? Oxygen is 21% of air. So if you should do your ratio, you will be getting this amount of air. So that becomes the flow rate or the number of moles of air that we need to use if we are using 100 moles of natural gas, right? So these preliminary calculations are important before we now start the simulation itself so that we know the flow rates that we need to use for the simulation. Okay, so we can start something now. So we've already done our specifications. Let's try and put everything together. So we would have 2 streams that we are going to mix. We would have a stream for the natural gas and then a stream for the air. This would be our natural gas. We'll label it as NG. Then this would be our air. Please, in the course of the discussion, if there are any questions, you can just prompt me. So we'll connect the natural gas stream and then the air stream, and then we'll have this to be the outlet for that. Now let's specify the natural gas stream. The conditions we are using, we were told that we are working at 20 bar, and then whatever is going to be coming into the reactor will come in at 30 degrees Celsius. So we can set our air and then our natural gas stream to those conditions, 20 bar and 30 degrees Celsius. So we'll make this 30, we'll make this 20. That's for the natural gas stream. And we are using, let's say, 100 kilomole per hour as our basis. Now, for the mole fractions, we're told that 90% was for methane, 5% was for ethane, and then 5% was for propane. And when we check, the total is 1. So kindly always check the total so that you don't make mistakes, right? Because there was a time that I made the zero 0.5 instead of 0.05. When you check the total and realize that the mole fraction is more than 1, you know that there's an issue somewhere. So always check the total so that you are sure that you've not made any mistake. So that will be for the mole fraction. That's for natural gas. And we can do the same thing for air. This is 30 degrees Celsius. This is 20 bar. And then the flow rate, the mole flow, the value we had was 2023.81. So put that here, 2023.81. Please, are we following? Please, are we following?
Yes, please.
Okay. So the mole fractions will have 0.21 for oxygen, 0.79 for nitrogen. So we are done with that part. We've put everything together into the mixer. Now the next thing is to now include the reactor. So we'll click on our stock and then place it down, and then connect our stream, and then we'll give it an outlet. Now, if we should double click on it, we can now do the specification. So for the first part, the question said we should work with it as though it was adiabatic, but then at the same pressure, right? So you're working at the same pressure. So the pressure is 20 bar. We can keep that value for pressure. But then if it has to be adiabatic, who has an idea of what we have to do? How can we make this adiabatic? Or if we say it's adiabatic, what does it mean? Or what are we expecting? Anyone? If we say it's adiabatic, what do we mean?
So gained by the system.
Please come again.
I mean, there is no heat loss or gained by the system.
Yes, that's correct. So then if that's the case, we would need to specify the duty as 0. If we make the duty 0, right, it means that we are not having any heat coming, any heat being removed, right? So then this will make it adiabatic. So that's what we do if we have to specify something as adiabatic in Aspen. Now, we'd have to go into the reaction tab and then specify all the reactions. So for our first reaction, we have methane and then oxygen, giving us CO2 and water, right? And we have the balance equations already here for us. So we can just put in the stoichiometric coefficients. So this was 1, this was 2. Remember, the negative is because it's a reactant. So Aspen does that automatically. And then CO2 and H2O, we had, I think it's 1 and 2 again. Yeah. So 1 and then 2. Now, just like we did the last time, you can specify the fractional conversion. Because we are burning it in excess oxygen, we expect all the methane to be converted. So we'll have a fractional conversion of 1 for methane, right? So we are having all the methane converted, a fractional conversion of 1 for methane. So it has to be between 0 and 1. If it's 1, it means all of it is converted, right? So we can do the same thing for the next reactions. And I think what would be easier is, okay, let's do it one by one. That will be better. So we'll do the same thing for ethane and then oxygen. We have CO2 and water. So if we should check the coefficients, it's 1, 3.5, 2, 3. Okay, so 1, 3.5, 2, and 3. So once again, the conversion is going to be 1 for ethane because we expect all of it to be converted if the oxygen is in excess. So for the last one, I'll just copy and then I'll change the value so that I don't have to do everything all over. So if you want to do that, you can highlight that rule, click on copy, click on paste, right? And Aspen does that for you. Then you can go into that specific one and then just change what you need to change. So I'll change this to propane. I'll change that to propane. And then the coefficients, it's 1, 5, 3, and 4. Okay. So this should be 5. This should be 3. That should be 4. So we are done with that one as well. Okay. So we have everything settled for the reactor. We can now run the reaction. So we can run the simulation and then we can check our results. So one of the things we will do is to check how much heat, oh, sorry, the outlet temperature. So remember, it was coming in at a certain temperature. That was around 30 degrees Celsius. If we run it adiabatically, we see the duty is 0. The outlet temperature is going to be that, right? So the temperature increased because the system was going to be releasing some amount of heat, right? So we would have that to be our outlet temperature. Okay. And we can check the stream results as well. So for that, we right click on the reactor, we click on stream results, and we can see what happens with the inlet and then the outlets. So this is what we have for the inlets to the reactor. This is what we have for the outlets from the reactor. So if we look at it, we see that all the methane, ethane, and propane have been converted. We don't have any of them in the outlet stream. And then we see some amounts of carbon dioxide and water being formed, right? So you can try this out. Now, the second part of the question said that we should do this when our temperature or the maximum temperature should be 1100 degrees Celsius. It shouldn't exceed it. So if we place that limit, that temperature limit, then we run it. That will be the highest temperature, or that will be the temperature as when we run it at. If we check the block results now, oh, sorry, I left the duty at 0. It was supposed to be temperature and pressure we specified. So let me do that again. Okay. So if we check the results now, the duty is no longer 0. There's a value there, right? So what that means is if we want to keep the temperature at 1100 degrees Celsius, we need to remove this amount of heat from the system. Because remember, the outer temperature was around 1200. So if you want it to be 1100, there has to be some kind of heat removal that we would do. This is the amount of heat we'll need to remove in order to get it at that temperature. But when we check the stream results, we would have fairly the same thing, right? It's the same um, conversion that we'll be having. So please, are there any questions at this point? Are there any questions at this point?
No, please.
Okay,
No,
that's
please.
fine. That's fine.
Okay, today, please, we
Yes.
are going with you. We are trying to relate it with you. So
Okay,
we
okay,
are
okay.
going a bit fast.
Sure. Is there any part I should go over?
No, please, but at least
Okay.
the speed.
So I'll give you about 2, 3 minutes to get to this point, then we'll continue from there.
Oh, I'm with you. I'm with you.
Oh, so I should continue.
Yes, please.
Okay. So we'll be moving on to the next reactor. But I think what we would do is I'm looking at the best way to okay, I think it's better if we finish everything under the reactors. Yes, when we are done with the reactors, then I'll point out a few other things for us to keep in mind. Okay. So once we have this down, we can save it. So we can save this and then let me save it as save it as this coming. Yeah, I think this should be fine. So when I'm done, I'll send it to the page, especially for this one not here. So we can open a new simulation. We are going to try a different example. So we can open up a new simulation. would have used the same one, but then the property method and then the components are going to be different. So I think it's best if we have a new simulation for that. So we'll close this one and then we'll have the new one opened. Okay. So for the next thing we want to try out, we want to work with, I think it was the yes, R Gibbs. So R Gibbs is the next reactor we are going to try working with now, right? And as we said, it works based on the Gibbs energy minimization principle. So it considers the possible products you can get, and then out of them, which ones are going to be more stable. And the thing about it is, R Gibbs works in a number of ways. So it can take everything that you have specified when you are choosing the components or when you are selecting the compounds. It can work with all of them, or you can limit it and tell it that consider only components A, B, C, and D, and then let me know which ones are more likely to be formed in which amounts and would we get them, right? So it considers the most stable species you can get, and the most stable species you can get out of the possible options you would have based on the temperature, pressure, conditions, any condition that you give to it. So it's actually a very, very effective block, especially if you are not too sure of what to expect, right? It would be very, very efficient for you. So this is the example we are going to try. We want to have a reaction between nitrogen and hydrogen to form ammonia in the presence of a catalyst. So we have nitrogen, hydrogen giving us ammonia. And we are told that the reaction is to take place at 450 Kelvin and 4 bar. First with stoichiometric amounts of nitrogen and hydrogen present, then with equal amounts of nitrogen and hydrogen, and then an inert diluent. We are going to use argon as our inert diluent, right? So something that would be added to a reactant. It would dilute it, but then it's not going to take part in the reaction. So it could absorb some of the heat, reduce the temperature, any of these things, but it's not going to take part in the reaction itself, right? So the first thing we will do is specify our components or select our components. So we need nitrogen, hydrogen, ammonia, and then argon, right? So the reactants, the products, any inerts we have, and then we'll click on next and specify the property method. So for this one, we are using ideal, for example. We are treating them as though they were ideal gases. Then we can come to the simulation itself. Now, you can decide to use the approach we've been using all along, where we have maybe two streams, you mix them and feed them into the reactor. That's fine, right? But you can also just decide to work with a single stream and then have everything specified in there. So this is going to be our feed. And then for this feed, the conditions again, sorry. So 450 Kelvin and 4 bar. So we'll make this 450 Kelvin, then 4 bar. Now, the first part of the question said that we are filling them in with stoichiometric amounts of nitrogen and hydrogen. So what that means is, based on this balanced stoichiometric equation we have up here, what we have up here, if we feed in 1 mole of nitrogen, we need to feed in 3 moles of hydrogen. That's what we are just trying to say, right? So you can decide to go ahead and do the calculation. You can select a basis, maybe 100 kilomole per hour, and then you now decide the fraction 0.25, 0.75. You can do that. Or you can decide to just go um do an easier path, right? So we know that if I have 1 mole of nitrogen, I need 3 moles of hydrogen. So over here under composition, instead of we working with mole fractions this time, we work with mole flow. And we just say that we have 1 kilomole per hour of nitrogen and we have 3 kilomole per hour of hydrogen, so that we know that it's 1:3 already. Right. So this time it's not a mole fraction, it's a mole flow. So we are not really bothered about the total being equal to 1. So please keep that in mind. Right. And once we do it this way, once you specify the mole flow over here, there's no need to do it at this part as well. So please remember that, right? If you specify mole flow here under the composition section, you don't need to do that over here under the specification section. If you had used mole fraction or mass fraction, right, then you would have needed to specify the total flow rate over here. So just keep that in mind. So we have that for nitrogen and hydrogen. Let's include the reactor. So we'll have our Gibbs. We place it down. We can connect it. and then we have the outlets. Okay. So now when we double click on the reactor, what conditions were we given? So 450 Kelvin, 4 bar. Those are the conditions the reaction is taking place at. So we'd specify the same thing, 450 Kelvin for temperature, and then 4 bar for pressure. Usually, if you are working with R-Gibbs, usually you may not really have to change what you see up here for calculation option, because R-Gibbs is going to do the phase equilibrium calculation and then the chemical equilibrium calculation, right? So it would do all of those things. But if you wanted to focus on just one of them, maybe just the phase equilibrium, or you wanted to be focused more on chemical equilibrium, but you're looking at a certain temperature approach, or you're working with a specific duty or something, you can make those selections. But in most cases, we don't really make any change to that, right? So you can work with it with this understanding. Then you can also determine that maybe you have more than one phase. If you should specify more than one phase here, you may need to add extra outlet streams to the block. So maybe you're expecting some liquid and some vapor phase, sometimes even a solid phase. You can have those extra outlets to do that, right? And you would now come to assign streams and now assign that, okay, this is for this stream, this is for that stream, right? So these are some of the things that you can do. But then most of the time, it's just going to be this way. Specify the temperature, the pressure, and you should be good to go. We can actually run the simulation now. But before we do that, I want us to also look at the products tab. You see that we have these options here. We have R Gibbs considers all components as products. What it means is that any components you specified here at the very beginning is going to consider that it can be a possible product, right? So if we have let's say the example we had previous, let's say we are burning a natural gas, you can have CO, CO2, you can have different things. Aspen is going to consider everything that you have in your specification as a possible product. It's going to consider that it is part of the things that you are considering to be formed, right? So that's one way you can go about it. The other way you can go about it is that you would identify the possible product. So you restrict it. So you tell it that no, out of everything we have, I don't want you to consider everything as a possible product. I want you to consider maybe just ammonia as a possible product, right? And you can select the phase. Is it mixed? Like as in it can be vapor liquid, is it just the vapor, is it just the liquid, what kind of phase do we have? The issue with this is you need to be very sure of what you are doing. You need to be very sure of the product and the phases, because if you don't do it carefully, Aspen will tell you that there's an issue with the balance, right? It may be considering what is coming in, the atomic balance of what is coming in, and it's not balancing with what is coming out, right? So that can be an issue. So if you would do this, you need to be very, very sure of your products, what you're expecting to come out, and then the phases as well. But as I said, in most cases, not all cases, but in most cases, we usually don't make any change to that. I'm just letting you know in case you ever encounter a situation where there are some components that you have specified that you are not expecting in your products, but then Aspen is still forming them so that you know how to restrict them. So now that we are done with this, we can run the simulation and then we can check the results. So we'll right click and click on results to check the block results first. So we see the outlet temperature. Let's change this to Kelvin. We started at 450. So it came out still at 450. Okay, that was the temperature we restricted it at. And this is the duty we would have, right? So in kilowatts, this is how much heat we had to remove. So let's think about this. It was coming in at 450 and we made it come out at 450. It means that for us to keep the system isothermal, we need to remove this amount of heat. 17.02 kilowatts of heat has to be removed for us to keep the temperature at 450 Kelvin. Now let's look at the things, or let's look at how much was formed. So we'll right click and click on stream results. And then if we check the mole flows, you see that the nitrogen has reduced, hydrogen has reduced. This is the amount of ammonia that we have formed. Please, is that okay? Please, are we here?
Yes, please.
Okay. What if we wanted to run it adiabatically like we did the last time? So we'll select heat duty, we'll put in a value of 0. So let's see what happens. So if we should run this, we see that the values have changed a bit. Right, so when it was adiabatic, we had less ammonia being formed. This is that fine.
Yes, please.
Okay. And we see that the outlet temperature went high. So it shot up to 572 Kelvin. So you see how temperature control is very important in reactive systems. Just 17 kilowatts of heat being removed give us a much better conversion at the end of the day. So these are some of the things you can try out in Aspen. You can test the things that you learn from temperature controlling reactors, and then you can apply them here. Okay, so let me change it back to the original temperature, run it, and then we'll save it, and then we can move on to the next reactor. So let's save this one, and then we can move on. Oh, I named them wrongly. The first one was supposed to be R stoic. I named it R Gibbs. Okay, I'll correct it later. So before I send it to the page, I'll change it from R Gibbs to R stoic. I'll use the correct names for all of them. Okay. So let's open up a new simulation. Okay. Okay. Please, are we here? Should we continue? Can we go on? Or is anyone still working their way around the previous one? Okay, I think we can continue. So for the next one, we have the equilibrium reactor, R equal. And as we said, it's used for simulating equilibrium reactions, right? So reactions where you have your system in some kind of equilibrium, especially when you have maybe vapor and liquid equilibrium. So, oh, we could have used the previous one. It's fine. So the example that we are going to use is going to be the same example, right? But then this time we're just going to try it with the R equal block. So we'll just quickly do the same specification, N2H2, NH3, and argon. And then we'll select ideal, and we can run it. Okay. So we have our feed once again. So we're using the same specifications. Okay, so this is 450 Kelvin, and this is 4 bar. So we have 1 and 3, like we did previously. And I think one of the things that we were supposed to do with the Gibbs reactor as well, it escaped me. We're supposed to try out the example when we had equal amounts of nitrogen and hydrogen. So we'll do that for this particular reactor, right? So when we have equal amounts of nitrogen and hydrogen and then an inert. So we'll do that for this example as well. So we'll just start with the stoichiometric amounts like we did earlier, and then we'll place the equilibrium reactor down. Now this time we'll need two outlets, one for the vapor phase, one for the liquid phase. So this one requires two outlets, one for vapor, one for liquid. So let's label them so that we can track what we are doing. So we come into the block, the same things we've been doing, 450 Kelvin, and then the pressure is 4 bar. And then we now specify the reaction. So it's similar to what we did for the R stoic, right? So we have our N2, we have our H2, we have our NH3. We are not expecting them to be solid, so we keep that side at no, don't change it. So N2, the coefficient is 1, H2 is 2, NH3 is 3, and we are done with that, right? So we can run the simulation and we can see what happens. There's an error somewhere. Sorry, 1 minute. Doesn't satisfy mass balance, so I might have done something wrong. I'm coming. Did I balance this correctly? Oh, okay. This is rather 3 and this is 2. I switched them. Okay. But please, I hope you saw the error that just came up, right? It mentioned that the mass wasn't properly balanced. right? So I had to come and check what I had done for the stoichiometric coefficients. Okay, so now let me reset and try it again. Okay, so now we have everything fine. So let's check the block results first, right? And realize that the duty is very similar to what we had for the Gibbs reactor. Okay, we can see the balance here. Yeah, so we have all these. Then we have the equilibrium constant as well. So this is a very, very interesting block you can also work with. Now let's look at the stream results. We should have something very similar to what we had for the Gibbs as well. So we don't have any liquid being formed. Everything is formed in the vapor phase. And that's fine. So we check it and we see these values. So this is the amount of ammonia we are producing. Now let's try out what we didn't do earlier. The second part where we're supposed to use equal amounts of nitrogen, hydrogen, and then an inert, right? So instead of we making this three, we'll make this one. So that is equal to what we have for nitrogen. And then we'll also have 1 kilomole per hour of argon, our inert. So I'll reset and then I'll run it again. And then let's see what happens. So let's check the block results first. That's here. So let's see the duty. So we have something a bit lower, right? We don't have to remove as much heat as before. We have something a bit lower. And then if we check the stream results now, we'd realize that we are having a smaller amount of ammonia than we had previously. Please, I hope that's fine. Can we see the differences? So this is when we
Yes,
have,
please.
okay, that's good. This is when we have equal amounts of nitrogen and hydrogen, right? Okay, that's fine. So I would save this as well and send it to us, and we can move to the next one. Now, before we move on, are there any questions so far? Any questions? No questions, that's fine. So the very last one we'll work with would be the R yield, and then next week we'll look at these other ones. These ones may take a little bit of time without really going into some details there. So for those ones, we really take our time and then we'll go into them. We'll look at the CSTR and then the R plug, those two next week. But even before that, I would try to get us an assignment on what we've done so far, and then we can pick it up from there. So let's have our final simulation. Okay. So for the final one, hmm, okay, we had similar results. That's good. Okay, so the final one, our yield. So for this particular reactor, you need to know the yield of your products, right? You may not really have information on the stoichiometry or the reaction kinetics, right? But what you will need is the yield distribution. So what do we mean by that? We are talking about how much we're expecting or the compositions we're expecting at the end of the day, what we're expecting in the products at the end of the day, that this is how much should have been produced from how much we fed in. Right? You're looking at the yields that we are going to get at the end of the day. We need to know that information. Usually, this reactor is helpful when you're working with processes like coal pyrolysis or pyrolysis of biomass, or whether you are dealing with something to do with proteins or starch from biomass. The reason we are looking at these things is because for these ones, sometimes you may not really have information on the stoichiometry, right, or on the reaction kinetics, but you may have an idea on how much yield you're expecting or the yield you're expecting. So this block becomes very helpful in those situations. Okay, so this is the example we are going to try. Iron is produced from iron ore through the reduction of hematites in the blast furnace. The composition and raw material and products leaving the smelter are provided in the tables below. The process requires coke, which is fed at a rate of 1 kilogram of coke per 10 kilogram of iron ore. For the purposes of this simulation, the operating conditions for the furnace are 1600 degrees Celsius and 10 bar. So we have the inlet composition the iron ore composition. We have the composition of the product. So these values here These are our yield distributions, right? And that's what we are going to feed into Aspen. So we are telling Aspen that, okay, at the end of the day, this is how much we are expecting for iron, the weight percent, based on what we were putting in, right? This is how much yield we are expecting. So just like everything else we've done, the first thing is that we need to specify all our raw materials and all our products. If there are any nets, we include them, right? So everything that we need in the simulation. So we'll do that one by one. Would start with what we have over here at this side here. So we have hematite, limestone, and sand. So let's do those ones. Fe2O3. We had SiO2, and then we had what was the last one? CaCO3. So remember, for certain materials or compounds, you can just type maybe their name or their chemical equation here, and Aspen would identify them. For others, you need to use the find feature, right? But once it's something Aspen can easily find, you just type it in and you should be good to go. It saves a lot of time. So we also need to include iron, wollastonite, coke, and CO2. So Fe. So we have Fe, CaSiO3. We had coke and carbon dioxide, so Ca and CO2. Now, over here, remember that what we are dealing with, you're working with iron ore, right? And all these things here are going to be solids. The coke is carbon, is solid. The only gas here is CO2. So we need to make sure that under the type, we change it from conventional to solid for everything except CO2. So I'll make all these ones solid. Then I'll keep CO2 as conventional. Because remember we said if it's conventional, Aspen considers it as something that can be vapor or liquid or vapor liquid in equilibrium, right? So we'll keep it as conventional. And then for our property method, we are going to select solids. Now, usually when you're dealing with solids in Aspen, you shouldn't be worried if you run it and you get results available with warnings. It's very common, right? It's Aspen is just trying to tell you that there are certain properties that may be missing. So there are some properties may exceed um some bounds that it has given to it, but it's because you are dealing with solids. So usually it shouldn't be a significant issue if you have warnings and you are still able to get reasonable results. So we are not really bothered about that. Now we can come to the simulation window and we can start our simulation. So remember, we have an iron ore and then we are adding carbon to it before we send it into the furnace. So we'll have one stream, we'll label this as ore, the iron ore, and then this would be our coke. So let's double it with C. Let's see. Okay. So for the iron ore, this is the composition we have. And we are using a pressure of 10 bar. The furnace is supposed to be at 1600. So we are taking it that it's going to come in at maybe atmospheric temperature, let's say 25. And then the pressure was 10 bar. It was 10. So the pressure was 10 bar. Right. When it gets into the furnace or the smelter, it will become wood, specified as 1600. And we can assume a basis. So let's make this 10. And we are changing it from mole to mass because here we are working with masses, kilogram, kilogram, and then weight percent. So it's better to work in terms of the mass flow. Okay. Now the reason I'm using 10 is because from the question we're told that 10 kilograms of iron ore is going with 1 kilogram of coke. So that's why I'm using 10 kilogram per hour. So that's when it comes to the coke, we just specify it as 1 kilogram per hour. Now, the composition will make it mass fraction since we are dealing with the weight percent, and we can specify them. So the Fe2O3 was 70%, SiO2 was 20, and then the limestone was 10%. So 70, 10, 20. So that's correct. Then for the carbon or the coke, same temperature and pressure. Once again, we change this to mass and we use 1 kilogram per hour. And it's just pure carbon. So mass fraction will make carbon one, right? And as I said, we always check to make sure the total is one. So we are fine with that. Now we can mix them up. Let's mix them and then we send them into our reactor. So the ideal thing to do is to, since we started at 25 degrees Celsius, we can heat it before we send it to the reactor. So we can do that. But even if we don't add this block and we specify the reactor at the temperature, Aspen will do what is required for us, just to make sure that we are not just feeding it in that way. We can just heat it before. Oh no, sorry, it's even going into a furnace, so we don't need to worry about this part. We'll just put it into the reactor. It should be fine. So under the reactors, we'll pick our yield, place it down. We have our inlets and then our outlets. So just like everything, we'll double click on the reactor. The temperature is 1600 degrees Celsius. The pressure was 10 bar. And then we specify the yield. So you see the yield tab up here. So what we do is that we select all the components we expect in the product stream. So we expect iron. We expect, I think this was the wollastonite. We expect carbon and we expect CO2. And we're doing this on a mass basis. So we change it from mole to mass. This is mass, mass and mass. Okay. Now for the basis yield, we are going to put in these values. So we divide this by 100, we divide that by 100, we divide this by 100, divide this by 100, so that we get it um, as a fraction, right? Not as a percentage. So this will become 0.445. And then the wollastonite was 0.233. The carbon was 0.019. And then the CO2, 0.303. Okay, so we can run the simulation. We may get warnings, but that will be fine. You can decide to even check what the warnings are. Or they said that something is not okay. Yeah. So sometimes the reason why you get that is that sometimes Aspen is extremely particular about the values you use. So if we sum what we have here 0.445, 0.233, 0.19, 303, we'll get one. But sometimes as when we be considering like extremely small decimals, like sometimes we need to make this 4444449 or something, right? So that's why you may have some of those issues. But then if we should check the stream results, realize that what we have is still fairly good enough. So let's check the stream results. And we'll check the mass flows. So this is how much iron will last tonight, carbon, and then carbon dioxide we are going to get produced. Okay, please, are there any questions at this point? I think the values are quite similar. So for this one, the basis was 110. We used 10 and 1. So 25.63 will correspond to 2.563 for the wollastonite. And then for the coke, 2.09, that will be 0.0209 for us. Then iron, we had 4.895. So from the slides, we should be getting 48.95. That's fine. Carbon dioxide was 33.33. So we would expect 3.333. So it's the basis we used. That's why it's divided by 10. Right? But we are getting the same thing that we are expecting at the end of the day. So please, are there any questions at this point? Any questions? Okay, I think that's fine. Okay, so if there are no questions, then we would end here for today. We've looked at how to use the first four reactors. Next week, we'll take the last two. And next week, we may need a little bit more time. So can we start at 7? Because these ones require a lot of details. So can we start at 7? Okay, sure. I think that's fine. So we'll start at 7 next week. Okay, so thank you all for your time.